Hello everybody, this is Dr. Groves. Welcome back to another video. In today's video we're going to be talking about osmotic pressure. So, first things first, what is osmotic pressure? Well, osmotic pressure is a colligative property that will occur when a solution of higher and lower concentrations are separated via a semi-permeable membrane. Essentially, a semi-permeable membrane that will allow solvent to pass through, but not our solute to pass through. Now, this particular process I'm sure you've heard about is known as osmosis if you've taken a biology class. Whenever we're talking about osmosis, we're looking for a net flow of solvent into the more concentrated solution. Now, this particular movement causes a pressure difference known as the osmotic pressure. So whenever we're dealing with osmotic pressure, we have a net flow of our solvent. Notice, we're only saying flow of solvent. Now, whenever we have this flow and this pressure, our osmotic pressure will be the same as the pressure that must be applied to prevent any net movement of water from solvent to solution, i.e., going from a low concentration to a high concentration. Now, that's a lot of words. Let's see what one representation looks like in a figure. So, looking at this figure here, we have our pure solvent in blue and our solution in green. And we have our semi-permeable membrane at the bottom part of the U-bend, shown here. And we have a net movement of our solvent going from left to right. And looking at subfigure A, we could see the solute molecules are not moving between the semi-permeable membrane, but the solvent molecules are moving either to the left from the solution to the pure solvent or going from left to right from the pure solvent to the solution. Now notice, over time, going into B, the rate in now is equal to the rate out due to their difference in heights. So essentially we've come to the point where there's a volume difference. That volume difference, when we look at the difference in the volume heights, we can tell there's a difference in pressure here. That difference in pressure is what's known as our osmotic pressure. And just as we said in the previous slide, the pressure we would need to put down onto our solution to stop this net movement, we have our osmotic pressure here. We put that pressure down on our solvent. There is no movement. We maintain our heights of volumes originally. Now, using this particular process and what osmotic pressure is, we can use it to relate to a variety of different things. So, to quantify osmotic pressure, we know the osmotic pressure, our symbol here, is going to be proportional to the number of moles of solute particles in a given solution volume. And our moles of solute over a liter of solution sounds like molarity, and that's exactly what it is. That's what our big M is here in our equation here. R is one of our many constants that we're going to use throughout the quarter, and it's going to be 0.0821 liters atmospheres per mole Kelvin. And T is going to be the temperature in Kelvin of your given solution, where M, big M, as we said, is going to be molarity, which is moles over liters of solution. So, there's a wide variety of different ways to deal with this relationship in this equation. One of the ways we could use it is to be able to find molar mass of a wide variety of different substances. For instance, biochemists have discovered more than 400 mutant varieties of hemoglobin, the blood protein that carries O2. A physician dissolves 21.5 milligrams of one variety into water to make 1.50 milliliters of that solution at 5 degrees C. She will then measure an osmotic pressure of 3.61 torr. What is the molar mass of the protein? So we know we're using our osmotic pressure equation. Our osmotic pressure is equal to molarity, R, and T. So now that we have this problem, what do we know? We have our osmotic pressure is equal to molarity times R times T. We know our osmotic pressure is 3.61 torr. We know our volume 1.50 milliliters. And we know our temperature is 5 degrees C. We also know that our mass is 21.5 milligrams of our sample. We have our relationship here. We can rearrange and solve for the molarity of our given sample. When we do that, we have our osmotic pressure over R, our constant, times our temperature in Kelvin. But our osmotic pressure is in torr. Based on the units for R, we need it in ATM. So looking at our handy-dandy equation sheet, we know that for every 760 torr, there is 1 ATM. And to get from centigrade to Kelvin, we use the conversions factor of 273.15. Plugging all of that information in, once we do that, we were able to solve for the molarity to be 2.08 times 10 to the negative fourth molar. And we remember that molarity has the units of moles of solute over liters of solution. So to find the amount of the solute, we'll take a molarity, multiply by the volume of the solution that we were given. But our volume was in milliliters. We need to make sure it's going to be in liters. So the 2.08 times 10 to the negative fourth molarity times 1.50 milliliters divided by 1,000 to get it into liters. We end up with our moles of our given solute. Now, we have moles of our solute. We were given grams, or at least a form of grams of our solute, as 21.5 milligrams. We're tasked with finding the molar mass of the protein. So we remember that molar mass is grams over moles. We have grams or milligrams that we convert to grams, divide by our total number of moles, and we can find the molar mass of the protein, which we come out to be 6.89 times 10 to the fourth grams per mole. Notice, that is a very, very large number compared to most of the molar masses we've been dealing with. Things we have to consider with this is that proteins are huge molecules. Many, many different elements that are coming into play. So a molar mass this large is actually reasonable. All right. Well, that's going to be it for osmotic pressure and for this video. And I'll see you in the next one.